Okay, so today, awesome day, guys. Do you recall, all right, do you recall this pretty simple limit? Yeah, Colin. Yeah, very good, super. So how did you do that?
I factored in my head x plus 2, x minus 2.
Yes.
Over x minus 2. Cancel.
And then you can just plug in.
Nope.
Okay. So, perfect. Now, remember we started the year with this because calculus are limits. And it was, you guys got terribly horrible, awful, rotten problems where you would do a lot of algebraic manipulation. And inside, Miss Jenkins is like, because there's a really easy way to do this, but you had to know how to take derivatives. So this is where calculus really saves the day. Calculus is going to make your life so much easier. We love calculus, don't we? So it is called L'Hôpital's rule. Pretty brilliant French mathematician.
Say it again.
L'Hôpital. You guys know French, I don't know. Hôpital. It is literally the hospital, isn't it, in French? Yep. But no S and that little funny thing over that little crown over the O. So, now, you guys you will be shocked and awed by this rule. And I'm going to show you a baby proof of this rule, just to convince you that it's true and why it works. If you want an honest-to-God proof of this that works in all cases, that proves it definitively, $1, okay, I'll give you a candy, whoever can guess, what does it use? What did I tell you, like, the theorem that they use for everything?
Mean value.
Yeah, I have your candy, mean value theorem, and also squeeze theorem. Or if you want, you can do a delta epsilon theorem, which I don't want to do. So, yeah, those are Alex's favorites, really?
No.
Okay, yeah, they're brutal. So if you want a really robust, complete proof of this, you can go online for sure, be my guest. I'm going to do a baby proof, is that okay? Awesome. So, watch this. Calculus substitutes what could be a tricky problem with easier substitutions. So do you guys agree this is a rational function, right? We have an f of x over a g of x. It doesn't have to be a polynomial over polynomial, so it doesn't have to be rational. But we have f of x over g of x. So what calculus says, and forgive this notation, it says if you take the limit of this, f of x over g of x, and you get, I'm going to start baby, then I'll get bigger, you get an indeterminate result. 0 over 0 is a meaningless result to us, right? If you get 0 over 0, or infinity over infinity, which you can rewrite to be 0 over 0, then you may do this. You may substitute. So if this, you may substitute, and this is crazy, with the limit of the derivative of the numerator divided by the derivative of the denominator. Not quotient rule. Not quotient rule. You are evaluating the derivative of the top divided by the derivative of the bottom. Let's watch it in action. So I'm going to plug this in, and really, you guys, on your homework, I want to see this, because L'Hôpital's rule does not apply unless you get this indeterminate form. It doesn't work, and I'll show you why in a second. 0 over 0, put a little check. Show Ms. Jenkins that you verified that it is a candidate for L'Hôpital. And now, you now know that that is equal, I'm kind of running out of room, is equal to the limit, as x goes to 2, of 2x over 1, which is 4. Much easier to deal with this. It is so simple, and last year, I don't know, I was helping kids prep for the mid-year, and I let it slip. You guys know Layla, right? I was like, Layla, she's like, oh, this is a really hard limit. I'm like, Layla, just do this way. And she felt so guilty, because on the mid-year, she used this. I know, and she said, Ms. Jenkins, it was so much easier using L'Hôpital. So I don't know, I kind of wish I taught you this before. Now, we changed the mid-year, so there was no.
Why didn't you?
Like, why isn't this taught?
Why is it in chapter 10? I don't know.
Why wouldn't we just always learn this
I
early?
know. Well, I can't teach it while we're doing limits because you haven't officially learned about derivatives yet.
Oh.
That's why.
We had learned about derivatives.
Yeah, you have to learn limits to learn about derivatives.
Yeah, we knew what they were.
I know, because 3P kind of started you on calculus, but not, like, we started as if that was first semester, freshman year, Calc 1. All right, so now why does this work? Well, do you guys remember linearization? I hope you remember that from mid-year. Yeah. Did you study that? So,
Oh no.
yeah, we have to use linearization, but it's not so bad.
Oh.
So, if we have,
Wait, you're using an approximation to prove something?
no. So here we have my f of x, right? And if I have a point, and I make a line tangent to that point, and let's call this, let's be original, x f of x, whatever. So do you agree that when I plug in x to the function or into the tangent line, I'm going to get the same result? Aren't they the same point at that tangent point? Right here, this point, well, let's call it a comma b, if you don't like that, a comma b. If I plug in a to my tangent line, I'm going to get b, right?
Yep.
If it exists, if it's continuous. And if I plug in a to this function, I get b. Do you agree that the limits are the same if they're both continuous? Is the limit going to be the same?
Every time.
Of course, right? So that is what we're doing. We're actually going to take the tangent line, linearization.
Wait, is that the proof?
No, because it doesn't work here. I'll show you why it has to be 0 over 0. All right, so that makes sense. You guys understand why I'm going to substitute out for the function the derivative. But now here is the caveat. So remember I told you you have to get that the limit has to be 0 over 0, right? And I'm going to change this as x approaches some a. So why is that true? Well, if I look at f of x, let's draw now. I got multiple colors going here. So here's my f of x. I plug in a, and what am I getting?
F of A,
0, f of a, which is 0, right? So a comma 0. And I'm plugging in to some g of x. We don't know. Oopsie. Supposed to. Oopsie. Touch. So what happens to g of x when I plug in a? Too many pens. 0. So don't they actually, if you look at them independently, not as a ratio, but don't they both cross, have an x-intercept at a?
Yes.
Right? That's crucial for what we're about to do. Because remember,
you're right.
let's make this a, sorry. Linearization, right? Slope of the tangent line,
Uh-huh.
right?
Yeah,
Good. So what does f of a equal? 0. This is why it has to be 0, because now watch what f of x equals. F prime of a, let's just change this to be x minus a. And I do the exact same thing for g of x, right? G of x minus g of a equals g prime of a x minus a.
Whoa.
And that turns to 0.
I see what's happening.
You see what's happening? So now,
It's time to divide.
if they equal 0, can't I replace f of x with this?
Yes.
So I'm going to do it right now. Watch how cool.
In cool in a second.
G of x, I'm going to replace with this. And that's enough to get you guys convinced.
Yeah.
Yeah, right? Oh, it's pretty beautiful. Oh.
No.
So it is really true. Now, this doesn't apply to the case of infinity over infinity. I'll talk about that in a second. And that doesn't apply to when x goes to infinity. For that, you have to get a more robust proof. All right, this is for x going to a, but this also works for x going to infinity. And I'll show you an example.
You're saying you need to tweak the proof, or
You need to just,
tweak what you did?
this is a nice little conceptual proof for when we're going to a point A.
Okay. Gotcha.
Yeah.
So, could you go further and do double derivative?
Yes. Very good. You're so smart. How do you do so smart? Very good. Sounds like
Be able
great.
to do it as long as you want.
Yep. Long as you keep getting 0 over 0, you have to check every time. Is it 0 over 0? If it doesn't get 0 over 0, you need to stop. Yes.
Why did you, so you know you like x minus a, you like f prime a times x minus a?
Uh huh.
Didn't you get rid of the a before, so what?
My x minus a over x minus a was 1. That.
Why does that, I mean, it doesn't matter because they cancel each other out, but why do you have to keep it as x minus a?
We don't know what a is. We can't make that 0.
Then how did you get rid of a before?
F of
Oh,
A
because
is
it's f
zero.
of a, it's f of a is 0, okay.
Okay. All right. So let me do just 3 examples, and then you guys are gonna practice. And it's a mellow night. This is actually a pretty lovely, day to do. So here's a classic example. You don't have to do it on the class. You can do it on the classwork. I think it's number 1, or you can just write it in your notes and excuse yourself from the classwork. It is
Sin x of
the limit. Yes. All right. You guys were so good. You made me proud. People when we were studying for the mid-year, ever remember what this was, right? What is it? 1. Good. So now, do this please. Plug in. What do we get? 0 over 0. Check. I'm good. I can use L'Hopital. Right? So now, this is exactly equivalent to this. What's the derivative sign? Cosine. Please don't make that fool's errand. Don't do quotient rule. That's not what this is about. We're not taking the derivative of this whole function, right? We're taking the derivative of the numerator, dividing it by the derivative of the denominator. What does that equal? You got it. Just like that. Do you see how easy tonight's homework's going to be? Right? I know. All right, I'm erasing. If you missed it, you missed it.
Wait, I missed it.
Ah, you gotta figure out on your own.
Wait, didn't you say,
Sorry, Alan.
wait, did you say infinity over infinity or infinity over 0?
Yeah, I'll show
It
you.
doesn't work?
Infinity over 0. Infinity is like the same as 0.
Yes. So 2.
Because
Because it's like, yeah.
the reciprocal.
This cosine of 0 is fine.
Wait,
it's
what,
fine.
wait, which indeterminate form doesn't work?
For now, today's lesson is just 0 over 0 and infinity over infinity.
So do you like infinity?
Well, I'll show you
Zero
on
to the zeroth
L'Hopital rule
power.
day 2. I'll show you other ones. Okay. So here we go. I told you guys we're gonna take 1 to infinity, but L'Hopital's rule still works for this, as long as I get 0 over 0 or infinity over infinity. So what happens? What's the ln? Well, what's this? Infinity, right? I mean, we can't really plug in, but we get this indeterminate form. But isn't this the same? Can't I put this as 1 over x divided by 1 over ln x?
Yeah.
Right? So now, if I take the limit, they're equal. Well, what is this limit?
0 over 0.
0 over 0. So do you see why I can do this?
So you could still do with the derivative, right?
That's right, but we don't want to do the derivative of this. We want to do the derivative of this. It's so much easier. Don't do the derivative of these. You see what I'm saying? So if you get infinity over infinity, just in your head, say, I can rewrite that to be 0 over 0, for sure. Okay, so I just wanted to show
That's
you.
just the proof, right? That was the part of the
Yeah,
proof you need to
you don't have to do that. As soon as you get infinity over infinity, you're like, check.
Oh, that shows
But is that in the full
okay.
proof is just the part of the proof
L'Hopital's
saying
rule,
that?
if you look it in the book, like this is,
It just explains how that's the same as 0 to 0?
yeah, indeterminate forms of 0 over 0 or infinity over infinity. So now, we know because of that, we can take the derivative, and now look how trivial this is. Oopsie, Miss Jenkins almost took the wrong derivative of x.
No good.
That would be bad, especially when I'm on tape.
Which is
So, so what do we get? Limit as x goes to infinity of 1 over x, what is that? 0. So the moral here is that ln of x grows much, much slower than a line. And this is where we're headed after February break. We're going to start to think about comparing different functions. So if you think about the graph, you know, we have this, and then we have this. So as x goes to infinity, this becomes inconsequential compared to just a line. The values, the way it's
It's like
changed.
something we didn't really like zoomed out.
Yes. Mm-hmm. Yeah.
What is
So
v equal to?
What's E numerically?
2.71828, 18284590545.
Better get it
Oh, you
right,
didn't want
Miss
that.
Jenkins.
Level.
So you didn't want that.
All right, one more example, and then you guys are on your own. The limit, let's do x over e to the x as x goes to infinity. Okay. So again, what are we getting?
No words. Infinity of infinity.
Uh-huh. Now let's do squared. Can I switch it up?
Yes.
So,
Instead of the nth power.
yeah, so this is addressing, who was this morning that got candy for this?
Not Ramon.
Jing? No, Ramon. Oh, so smart. So, we can use L'Hopital with this, but you see, the first time we do it, what happens,
Is that just right on my lips? Alright, good.
we're no better off, right? So, but you have to check, do you still get infinity over infinity? You can take the second derivative and the third, as long as you keep getting 0 over 0, or infinity over infinity. And now you see what happens. 2 over e to the x equals what? Right. So exponential functions grow much faster than a polynomial. Always true. And think about the graph. We have parabola, and then we have exponential. World of difference. Maybe not so much near 0, but wow, big difference when you get out to infinity. Okay, you never get there, but. All right, so that is it. You guys have fun. You have about half an hour. Thank you so much. Love this class.